Good afternoon, everyone. I am Jukka Vesa. I am the sales engineer for the Nordic region, and today is the first of two technical switching webinars that we are doing. The topics are chosen based on a survey we sent out and basically decided by you guys, our resellers, is what technical switching features do you want to learn more about. So, without further ado, today's topics are VLANs and VLANs, virtual LANs, and spanning tree protocol. If you have any questions, please put them in the chat or question section, and I will do my best to answer them. And yeah. Without further ado, let's start with a virtual local area network, or VLANs, what they are and why should almost each and every one of you use them. So let's first start off by explaining what is a broadcast domain or a local area network. Broadcast domain is a logical segment of the network where each and every computer can see and communicate with each other. And this is happening on a layer 2 level. So basically the devices only care about each other's MAC addresses at this point. So in this example, we have two broadcast domains which can't see each other, but the devices inside both broadcast domains can. So you would need a router or a layer 3 switch for these two layer 2 broadcast domains to talk to each other. So what is VLAN? A virtual local area network, actually. There's a typo on the slide. So it is a way for us to split the physical network into logical segments by using the same devices, using the same cabling. Meaning that in the example on the left-hand side, we have a physical broadcast domain. So all the devices connected to each other physically are able to communicate with each other. On the right-hand side, we have separated the network into three different VLANs, VLAN 10, 20, and 30. And computers or devices that are connected to these virtual local area networks are not able to communicate to the other VLAN, but are able to communicate within that same VLAN. So different VLANs cannot communicate with each other is the prime example. So as an example, how can we use VLANs? In this example, we are just VLAN 10 servers, VLAN 20 laptops, VLAN 30 access points. A most common or a more common example would be that we have VLAN 1 or something as a management VLAN, and then on top of that we might have VLAN 10 for employees and VLAN 20 for guests, or however VLAN numbers are something from 1 to 4095 basically. So VLAN numbering is irrelevant. You can use whatever you want. So what are the benefits of using VLANs? We are able to increase the network performance by segmenting the network. So we are reducing the size of the broadcast domains, meaning that less devices within that broadcast domain are able to hear that broadcast message. So we create less traffic inside that physical network, basically. We limit the distribution of the broadcast messages. Flexible network segmentation. So as said, we can segment the network per functionality or something like that. So employees, guests, IP phones, servers, DMZ, whatever we choose to do. Simple management. Configuring VLANs isn't really that difficult when you understand kind of how they work. Enhancing network security. from the guest network you can't see in the employee network or vice versa. So you are, once again, by limiting the broadcast domain, you are able to limit what the devices are able to see in that network. Reducing costs, of course, since you are able to use the same devices transmitting multiple local area networks, you don't need multiple devices to do the same thing. For example, you can use one switch to distribute how many VLANs you wish. If you would do it physically, you would have a switch per network, employees, guests, servers, etc. All right. So Zyxel supported VLAN types. So first of all, tag-based VLAN is the topic of the day, which we are going to in detail to check what it is and how it works. And the reason behind it is that it is vastly the most common type of VLAN used. The other ones, subnet-based VLAN, which is based on the it bases on the client IP address to put it on a certain VLAN. Protocol-based, by traffic by protocol is being transmitted to certain VLAN. MAC-based, so by MAC address, or port-based by physical port on the switch. For example, ports 1 to 6 are going into VLAN 10 and 7 to 10 are going into VLAN 20 or something like that. All right. So tag-based VLAN is the type of VLAN we are talking about today. So what is a tag-based VLAN and what is the clear benefit of it? It can travel to multiple switches and multiple devices, including access points. Every device that supports tag-based VLAN, basically, and gateways, etc. It basically adds just 4 bytes to the normal MTU, making the MTU size basically 1522 bytes. And of course, switches that support VLANs need to support a frame this size as well. So in this scenario, we are transmitting VLAN 10 and 20 through several switches, and devices in switch A VLAN 10 are able to see devices in switch B VLAN 10 and VLAN 20 to VLAN 20, etc. So they become, even though they are connected to 2 different switches, they are in the same broadcast domain, which means they are able to see each other. Okay, so the tag-based VLAN can be split into the 3 different processes. You have the ingress rule, the forwarding process, and the egress rule. So when the switch receives a packet, it first is being classified by the ingress rule, then determined by the forwarding process. Am I allowed to forward this or not? And then the egress rule, how am I putting out this traffic? So now in more detail, what these actually do. So if the ingress rule, so if the frame already has a VLAN ID on it, so the frame is tagged, we already know that it's a part of VLAN 10 or 20 or whatever VLAN it may be. So we do not need to put a tag on it because there is a tag already in it. Untagged traffic is traffic that does not have a VLAN tag on it. So there might be a device connected to that port that does not either support VLAN, or it's basically management traffic like requesting DHCP addresses or something. In this example, it's a laptop plugged into port 2, which would be untagged traffic. So the rule of thumb is usually that laptops, APs, management traffic, any device that is unaware of the VLAN IDs in that network will connect to that untagged traffic. And then it will hit the ingress rule, which defines that what is the VLAN ID of the ingress traffic. And if it's already tagged, then we know it, fine. If it is untagged, we need to put a VLAN ID on it. and there is a PVID value which we determine which VLAN should this ingress traffic be a part of. So, forwarding process. In this example, PCA is trying to communicate with PCB, and it needs to meet two criteria or two tables. First of all, it will check the switch's MAC address table. Do I belong in the same MAC address table as PCB? If yes, I am able to see that certain device. If that's an okay, then we move into the VLAN table. So am I allowed to communicate with PCB? If that answer is yes as well, then we are able to transmit traffic to PCB. Okay. Egress rule. So how do we put out that traffic? So at this point, we know it's a part of VLAN something, and PCB is connected to port number 3. So do we push out that traffic as tagged or untagged? If it is a device that does not support VLAN tagging, like a laptop, for example, and yes, I know the Windows 10 supports VLAN tagging, but nobody actually uses them. So in this example, laptops will not use VLAN tagging. So we need to put that frame out as untagged for the PC to understand it. If this would be a uplink port between two switches, both switches configured as tagged, then we would put the egress rule as tagged. Or one example would be that if this port has an AP connect to it, the untagged traffic would be the management traffic, and the tagged frames on top of that would perhaps be the SSIDs. So employee and guest SSID wireless networks, for example. All right. So just first an example in our standalone switching and how everything actually works in there and what does each and every tab do. So we configure the ingress rule from advanced application VLAN configuration and VLAN port setup. The ingress check tab means that it will either allow or disregard any traffic that's not a part of that VLAN. PVID was the ID that determines the ingress traffic. If it's untagged, where do I put this traffic to, in which VLAN? Acceptable frame type, do we accept tagged, untagged, or all traffic? Isolation, if we enable layer 2 isolation on this port or not. So devices on MAC level are not able to see each other from this port. Something to keep in mind, don't put isolation on uplink ports. GVRP is for dynamic VLANing. So if you have, we are not going into more detail on this today, but if you perhaps use dynamic VLAN over an AD server or something like that, so your username is determining the VLAN you are going to be directed to, so that's GVRP. And VLAN trunking is basically a feature that just pushes through everything that's tagged. I am not a fan of VLAN trunking. It solves a lot of problems in short term, but it also makes fault finding incredibly difficult because you are not able to get a visualization of what is actually being transmitted through. Okay, and then the forwarding process. So we either select normal, which is for GVRP. The term is a bit confusing to me, but that's how it is. Fixed, so this port is a part of this VLAN ID, and we would define that VLAN ID under the VLAN group ID and have it active. Forbidden is that this port cannot transmit this VLAN traffic. And then the egress rule, simply is it tagged or not. So once again, between switches, usually tagged to end clients like laptops, usually untagged, to SSIDs in an AP, tagged, etc. So you pretty much need to know what device is connected to this port to have the correct tagged or untagged setting. All right. Then that was the explanation of tag-based VLANs, and then we will go and take a sneak peek of what it actually looks like in the switch configuration, even though there was a couple of slides already illustrating that. So is it alive? Yes, it is. So let's ignore that it can be put to Nebula. Something worth of mentioning that the XGS 1930 switches have a really nice startup wizard where you can do all your basic configurations like IP addresses, passwords, port protections, virtual LANs, quality of service, etc. So, for example, you can just select which ports are a part of which VLAN and how. But today we are not showing it the easy way, but we are showing it from the switch configuration itself. So as illustrated in the slide, advanced application and VLAN. So I have two VLANs in this switch currently. I have VLAN ID 1, which is the base VLAN that's already created in the base configuration, and then I have VLAN ID 77. And how do I create it? First, I do the ingress rule through VLAN port setup, and then I set the PVID, so devices that are being connected to ports 1 or 2. If the traffic is untagged, it will be directed to VLAN ID 77. All the other ports are on VLAN ID 1. So that's the ingress rule. And now the forwarding process and the egress rule. So we select the VLAN 77 and how it is set up. We are not using GVRP, so none of the ports are in normal status. Ports 1, 2, and 7 and above are fixed, so VLAN ID 77 is allowed on these ports. It is forbidden to join VLAN 77 in ports 3 to 6. And also the egress rule, since for these ports, for example, might be for laptops, we are sending the traffic out untagged. And all the other ports might be, for example, for access points, which it's for an SSID, for example. So we want to push out the traffic tagged, and for uplink ports as well. Okay, so not too complex. So let's check what it looks like from Nebula, our cloud managed devices platform. So we go to switch and switch ports. And then we select either one or multiple ports we wish to configure. And then we basically just set the PVID. So if this would be a wired connection like ports 1 and 2 in the previous example, we would set it as access and 77. So a laptop would join VLAN 77. If this would be a port for uplink between switches or to an AP, we would set the VLAN ID as 1 for management VLAN, and we would allow 1 and 77. So the management VLAN is allowed, plus for the SSID we allow VLAN ID 77, or the VLANs we used in the previous material as VLANs 20, 30, however you want to put it. So configuration of VLANs on switches are fairly simple. You just need to follow a path. So each and every port has the same or each and every port you want the VLAN to pass through has it allowed. Simple as that, nothing more. All right, any questions about VLANs at this point before we move onwards to spanning tree? Okay. Oh. So, spanning tree protocol. We are going to the basic spanning tree protocol. It is very similar as rapid spanning tree or multiple spanning tree, which the names obviously state the difference to basic spanning tree. We actually nowadays support only rapid spanning tree or multiple spanning tree on our switches, but the basics are the same and the idea is the same. So we will go through the basic spanning tree protocol and how it works, etc. So why do we need a spanning tree? So two reasons. First of all, prevent broadcast storms, and second of all, to give redundancy in looped scenarios, and of course preventing loops. So if in this example we would have a PCA communicating with PCB and they have two routes to go, two different ports are connected between these switches, and then the since there is a loop, the traffic will start going through that loop once and again. So you will create a broadcast storm and create unnecessary traffic, which can be, in the worst example, it can actually crash your network if it gets too bad. There are ways to limit this other than spanning tree, but this is one. And the second reason is that MAC address databases on switches in these kind of scenarios would include the MAC address if PCA is trying to talk to PCB, and both switches are connected through ports 3 and 2, so PCA would see PCB in both ports and would be unaware which way to communicate to PCB, and that can create issues as well. All right, so a lot of text in this slide. So just the terminology that we are going to talk about and what does it actually say, or what does it actually mean. So PBDU means Bridge Protocol Data Unit, and the priority IDs of that switch, it's used to define the priority IDs of switches and calculate path cost. So configuration of PBDU is to find a root bridge. So if you imagine a tree, it's a spanning tree protocol. Tree is a good example. So you have a tree trunk, which everything should flow through, and then you have the branches, which are your switches somewhere, your access switches in your network. So to find a root bridge, find the tree's root and find the selected designated switches for each segment, so each branch. And so we can also break up a loop situation. So if switches in the branches are connected directly to each other, the traffic will not start flowing through a loop, but it will be directed to the root of that tree. And then we have the topology change notification, or TCN, which is there for if something changes. So if something in the topology changes, somebody connects a cable or disconnects a cable, or a device breaks down or something like that, you are able, the spanning tree protocol is automatically able to adjust the routes used to prevent network issues as small as possible. So only a part of the network would go down. So a new route would be defined. All right, then in a bit more detail. So just some ground rules with spanning tree. So just one root bridge is allowed, and one root bridge only. And on the non-root bridge devices, only one root port is allowed to that port. So a dedicated port which is connected to that root bridge. And one designated port per segment. So only one way to transmit that traffic. And a non-designated port will be something we call a blocked port, so traffic will not flow through that port. Okay, so how do we elect that root bridge? So which switch will be the root bridge? It basically calculates the bridge priority, which by default is 32768, but this is adjustable, and when you are doing spanning tree, you always should adjust it. On top of that, it calculates the MAC address of that switch, so which switch has the lowest MAC address, and of course in a network you can't really plan for that usually, so that's why you need to change the default priorities. So this is the way to determine the root bridge switch. So in this example, for example, the switch A MAC address ends in 111, switch B 222 and 333. So switch A with the lowest MAC address will become the root bridge. Fairly simple process. All right, so on top of that, we calculate the path cost for the switch. So which route should we take, which has the lowest path cost? So you can basically ignore the previous part of it because it's not valid anymore, but the cost for 10 gigabit link is to 1 gigabit for 100 megs 19 and 10 megs 100. So for this type of scenario, switch B would have a root cost to switch A of 19, and between switches B and C also 19 because there is a 100 megabit link, and between switch A and C only 4 because it is a 1 gigabit link. Basics of that. So to define the root port, we would define in switch B, for example, the port 3 as a root port because it is connected to switch A, and in switch C, root port would be 5 to connect it to switch A, and these would be defined as designated ports in switch A. So we can calculate the path cost to the root bridge based on these values. So for example, switch B, if it would go through switch C, would have a root bridge cost of 23, so 19 because of the 100 megabit link and 4 because of the 1 gigabit link between switch A and switch C. And of course, the other way around, if it's 100 and 100, it's 19 plus 19. These are more relevant in bigger networks, but you hopefully get the idea with just an example of switch 3 switches. All right, so with the path with the highest cost will have a blocked port in it. So in this example, the block port is port number 6. And that will disregard all traffic and then preventing a loop, hence preventing a broadcast storm. So if something changes, for example, the blocked port in this example, the path cost will also change, calculating it once again and possibly changing the route to another, or the data traffic through another route. Okay, So spanning tree port status can be any of these. So basically, if you see a spanning tree port status being blocking, it's only allowing to receive BBDU traffic only, or BBDU frames only. If it's in listening mode, it is allowed to receive and transmit BBDU traffic only. If it is in learning mode, it is able to receive and transmit BBDU traffic and also allowed to learn MAC addresses. If it is in forwarding state, it is allowed to send and receive traffic as normal and learning MAC addresses, etc. So normal port is basically in normal functioning order. And disable would be that it's administratively down, so somebody has shut the port down. Okay, edge or non-edge port. So in this example, we have defined an edge port for a PC. So spanning tree will always be in forwarding state at this point. So immediately when you do the setting change, it will change to forwarding mode without going through the process we saw in the earlier slide. So non-edge ports will be basically uplink ports with spanning tree enabled, which is going through that state we saw, or that process we went through on the previous slide. Okay, so when something changes, so when a bridge sees a topology change, in this example, the blocked port will change, has changed from port 6 in switch C to switch B port 4. So switch C will send a TCN to root bridge as a unicast message that something changed. My port 6 is no longer in blocking mode. And then switch A, which is the root bridge, will send a multicast TCN message to all switches in that environment, letting them know that there has been a change in the topology. Please adjust your routes accordingly. Okay. So then the live demo part. So just once again checking the switching, where can we find these settings, etc. Okay, so spanning tree settings you can find under advanced application and spanning tree protocol. And as I mentioned earlier, we only support rapid spanning tree and multiple spanning tree protocols. We select is it active on a switch or not, and then we set the bridge priority. So if we know this is a root bridge switch, we are able to set the priority as low as possible. We can define the timers on the spanning tree process, where it defines the port status. We are able to set port by port. Is spanning tree active? Is this an edge port? The path cost is automatically determined. So this is an XGS switch. So 4 was for 1 gig and 2 was for 10 gigs. But of course, we can manually adjust it if we wish to. Priority is a setting that you are able to define in a looped scenario, that which port will go to shutdown mode first. So if you have several different routes to some location, by setting the priority of that port, you are able to set which ports will go inactive first before others. All right, so in Nebula, we have quite less settings that we can tinker around with, but on port-based, we have rapid spanning tree either enabled or disabled, nothing more. And when we are configuring the spanning tree on the switches themselves, we basically set spanning tree protocol on a site. And we just select a switch and give it the priority. And of course, in my demo environment, I have one switch, so the example is quite poor. But basically, if this would be switch number 2, I would give it a higher priority and going onwards and onwards, basically, through the tree up to the branches. So configuration, once again, fairly simple once you get the hang of it. Something to still mention about spanning tree protocol. So if you have a simple small office network, let's say you have 1 or 2 switches, you don't really need spanning tree protocol. If you have a big network, perhaps a loop topology for redundancy, then of course this is very valid and very valuable function for you. So pick and choose basically your environment that you're installing. Is this a valuable function? Spanning tree creates some broadcast traffic in the network. So the rule of thumb would be that if you don't need it, don't use it. If you need it, please use it, because it's a really good function in bigger networks and it gives you a lot of resiliency, especially if you are doing ring topologies, then it is more or less mandatory to use. All right. So far, we only have one question, and it is this seminar being recorded? Yes, it is, and you are able to download this afterwards. I will keep the webinar running for a few minutes. If there are any more questions, I am happy to try and answer them. But if there is no questions, you can of course contact me afterwards to jukka@zeisel.fi. But as said, thank you all for attending. If there are not any questions, feel free to go with your Tuesday afternoon actually and enjoy it. At least in here the weather is really nice. And also we are in this quarter, we are running promotions on our switches. So if you have a project or otherwise just wanna buy a whole heap of our switches, please do check out the promotions. So we have a couple of questions coming. Screen is so small. Okay, thank you, Dennis, for the feedback. Nice to hear that it's being good. And as said, this is the first technical webinar that we have done. Usually these are done in a classroom with people. So if there is any feedback on the webinar, I'm happy to hear it as well. From Eric, I found the first part about VLAN tagging too high level. Do you have a bit more down to earth article you could refer to? I will try and find one. As said, the material is very technical, very detailed. So I will try and find a more down to earth material and I will send it to you. I'll still wait a couple of minutes if there are any questions more. All right, there seems to be no more questions, so I will shut down the webinar. Thank you all for attending once again, and any Xyzer related questions, please just feel free to contact me. Thank you all for attending, and bye-bye.